Hi everyone, I'm Oriana Riva from Microsoft Research. I'm going to present Etna, a programming by demonstration tool for extracting action graphs from websites. This is joint work with my colleague Jason Case. Extracting machine understandable knowledge from the web has been a long-standing research goal. Techniques for automatically extracting entities from websites have been investigated extensively and have led to the creation of large knowledge bases such as Bing and Google Knowledge Graphs. These today include many millions of entities and billions of facts about them. For example, for a restaurant entity such as the one shown here, a knowledge base contains properties such as the restaurant website, its location, the type of cuisine, the year of opening, and so forth. Using this kind of data, knowledge graphs enable semantic search and many other useful user experiences. However, while lots is known about the entities that a web page contains, little is known about the actions or the functionality a web page supports. Such action-related knowledge could be used to support task completion in search or AI assistance. Our example restaurant website, for instance, supports the task of ordering food online. Ideally, we would like to be able to extract all actions involved in this task, including their input parameters. So in this example, this involves modeling the actions of selecting the location of the restaurant from which to order food, selecting which pizzas to order, choosing between the option of delivery or takeout, and completing the checkout process. Note that while the value of an entity fact lies directly in the information it stores, such as a restaurant phone number, the value of an action lies also in the output it generates upon execution. Therefore, besides extracting action labels and input parameters, it is necessary to support their execution. To this end, we propose Etna. Etna is a programming by demonstration tool to extract action-related knowledge from websites and to support execution of the extracted actions. From interaction traces in a target website, Etna generates timelines by classifying UI snapshots into states and UI events into inputs or actions. To support action execution, Etna also extracts parameterizable deep links and UI scripts. Then, from timelines, it generates an action state model of the website visualized as an action graph. Compared to traditional programming by demonstration tools for UI automation, Etna provides several key features. To illustrate them, we use a simple action graph extracted from the OpenTable website for making restaurant reservations. First of all, unlike tools like Selenium, Etna models application states at a fine granularity. Prior work classifies UI pages based on their names, such as activity names in the case of Android application. In Etna, states are classified at a fine granularity using various textual, structural, and visual features. For example, in Etna, an empty or a populated shopping cart are considered two different states. This fine-grained state classification is essential to reliably execute actions in dynamic websites. For every state, Etna extracts deep links and an aggregated knowledge tree. This knowledge tree contains various semantic information about the page UIs associated with that state, such as OCR visible text, schema.org annotation, the set of interactable UI elements appearing in the pages, Open Graph and HTML annotations, and so forth. A second key property of Etna is that it extracts generalized action functions with associated input parameters. Actions are parameterizable, as if they were service APIs. To achieve this, Etna introduces the concept of multi-input events, which allows to correctly model complex list selections, such as in nested lists, which are fairly common in modern web pages. Finally, compared to prior work, Etna provides more robust action execution. It does so by extracting parameterizable deep links that can recreate application states fast and reliably. Deep links are extracted by mining the collection of UI snapshots associated with a state. Some web pages, however, do not support deep links, or it may not be possible to infer them reliably. So in the absence of them, Etna falls back to UI event replay. And to deal with UI changes and dynamic content, Etna uses a new technique called semantic ranking. Semantic ranking locates UI elements for interaction by progressively limiting the search context using a large set of element attribute-based filters. But by searching for textual strings like a restaurant name rather than fixed attributes. A search-based approach like this one adds lots of flexibility by not predetermining where content is within the UI tree and makes action replay more robust than approaches that use fixed selectors, like in Selenium. Our paper contains an extensive evaluation of Etna, including the manual effort involved in building action graphs, the accuracy of action replay in dynamically changing websites, and the accuracy of UI state, UI snapshot and state classification. In addition to that, Etna was used to build several use cases. It was used to generate APIs for web data scraping. It was used to build a zero-coding framework for generating task-oriented chatbots. Using Etna, we built chatbots for making restaurant reservations, for looking up weather forecasts, for searching movies. We also use Etna to build more reliable RPA, robotic process automation. This is an application of UI automation that has seen tremendous growth in the last few years and where reliability is critical. Finally, we use Etna to generate datasets for NLP research in the context of a natural language guided agent for web navigation. Thank you for listening. Please read our paper for more details and feel free to reach out to us for any question. Thank you.